Hello, welcome to this new session of the GEOTOP A seminar. We have the great pleasure of having Wojciech Chacholski with us. He's from KTH in Stockholm, and the title of his lecture is Data, Geometry and Homology. Please, Wojciech.
Thank you. So I will entertain you today on behalf of the TDA group at KTH and our collaborators. Here are some of the names of these people. So my aim is to tell you a story about the strategy of how to explore geometry of data. So the reason we need data analysis is because of complexity of data that we face. This means that data analysis is about simplifying. It is essential that we forget a lot about information and retain hopefully elements that we might be informative to our problem. I mean, let's imagine the following experiment. You come to a room and you see little stickies with numbers on various objects. You see, I came before you and I put these stickers describing the length of these objects, except that I didn't put any unit. Now you come to the room and you have to guess what these numbers mean. You can do lots of experiments. You can measure it, you can weight it, and then after a while, of this experiment, you will come up with a conclusion that these numbers most likely tell you the weight of the object. And you might be 80% in this circumstance, you might be 80% or 90% correct, because maybe in your circumstance in your room, the weight is correlated to the length. So although you are wrong for all practical purposes, you might be correct. Okay, you might sort of think how much experimenting you would be required to do to actually come up with answer to that, to the meaning of these numbers. Now imagine that here you actually take your answers from a small set of possibilities. Maybe you might think about length, weight, color. But imagine that in biological sciences, for example, from a universe that it is not very close to us, you might even not have names for the phenomena that you see. So data analysis, it is essential. It's about simplifying. You have to forget a lot of information. Okay, and if you don't do that, then either your data is not so complex, or you still, convert something very, very complex into something almost as complex, and you don't get any more information. Okay. So, for example, consider something called high-C contact map. So, you see, when you look at the DNA strand and you make it flat, this is almost 2 meters long. So let's divide this strand into around 1 megabase. I'm looking for the name, segments. Okay, but when this strand is embedded into a chromosome, it is very tightly embedded. So you might want to understand the geometry of this embedding. So there is this high-C technology. What it does, it binds the segments which are close to each other. Then you cut the strand, and then you count number of connections between different segments. So that is a matrix of the size, symmetric matrix of the size 3,274 times 3,274. That's the size of these segments, which I will refer later on to as loci. Okay. Now this matrix is a similarity matrix, which means that high value of an entry indicates that these loci are close to each other. Okay, so here's an example. Here's an example of such an outcome for a neuron cell. in this particular for human neuron cell in this particular example. Now you might wonder, so this is the perception. This is how we measure something, and we know that it measures somehow the geometry of this embedding. So now you might sort of ask how we can use this view into this geometry of the embedding to understand the actual that embedding. Okay, but you maybe in terms we would like to find some aspects that somehow tells us that various loci are different, etc. Let me also remind you that different tissues can have different embeddings, even if you have the same DNA, but depending on the tissues, these embeddings actually differ. There are also known disorders that are related to wrong embedding, genetic problems caused by this wrong embedding. Okay, so the first step that a geometer like me would do would be to convert this similarity matrix into dissimilarity, or maybe a distance matrix, where it is so what is a dissimilarity matrix? It is a symmetric matrix with 0 on the diagonal, where small values indicate closeness. I convert this similarity into dissimilarity, into distance matrix, somehow because I feel more comfortable with them. Now, the way you can do that, there are several ways. There's not one way. Let's consider the following. Here, if this is contact map, I will define my dissimilarity matrix in the following way. So the following formula. So what you do, you start. It has a meaning. You start with embedding this strand, and then you look at the loci I, and you see what is the difference between connections of I with itself and the connections with the previous loci. Okay, that's one possible way of converting similarity into dissimilarity matrix. Okay, so now so it tells you some sort of proximity of loci, this dissimilarity matrix. So how would you actually visualize a dissimilarity matrix of size 3,700 3,700 something elements? Okay, so TDA pipeline is one possible way of understanding these such distances. Okay, so so in TDA pipeline you start with a distance. Now the first step you do in TDA pipeline is to convert that distance into a spatial information, and one of my favorite construction is Vietoris-Rips construction, which convert distances into a time series of simplicial complexes. Now, I don't want to get into details, but you might wonder, what is the purpose of that step? So first of all, the Vietoris-Rips construction doesn't forget or embeds any information. If you know Vietoris-Rips time series, you can recover the distance. If you know the distance, you can construct this Vietoris-Rips. So it doesn't forget or adds information, which means that it is not a simplification. It is not what data analysis is about. Okay, it's as complex as the original data, but it has one. So you might wonder, why do we do that? So it has one crucial property. So imagine that I have two distances on a set x and y, and I have some process that converts x into output of y. It could be, imagine, chemical reaction. You put some the only thing you observe, you put the input, and then you look at the output, and you perform one such experiment, and you get this function f that transports the input x into output y. And you have another, you perform the same experiment, and you do another measurement, g. Okay. Now, not every time you get exactly the same measurements. There are various factors that affect your experiment. So let's say, but typically you can assume that maybe these experiments are very close to each other. You know, these distances between these two functions are bounded. Okay, f is not equal to g. F is equal to g up to an error. Okay. Now, if this happens, so that's the nice thing about Vietoris-Rips. What happens if you apply at time t? At time t, these functions might be different. But if you move a little bit, if you allow yourself a little bit leeway and go to the next, you move yourself a little bit by this error. It turns out that these two maps are homotopic. Okay, these two maps are homotopic. In other words, the Vietoris-Rips construction converts noise into a homotopy relation. That's the key aspect of the reason why topological data analysis uses this Vietoris-Rips construction, because it converts noise into something that topologists have been studied for a long time, into homotopy relation. Okay? Now, this doesn't buy you simplification, because still to check that two maps are homotopic is very hard. Okay? So to make it even simpler, the next step is to convert this time series of simple shell complexes the time series of vector spaces by applying homology. Now, why do we do that? Is because homology has this homotopy topic, then homology of these functions is the same. So in other words, through this process, through those two steps, we convert noise using Vietoris-Rips construction into homotopy relation, and then applying homology into equality. In other words, what we achieve denoising. Okay, this effect of denoising is very crucial, and it's particularly useful when in the situations when there's a presence of noise. Okay, for example, in the outcomes of this high C technology, where you measure, you count certain connections, which can sort of depends on lots of factors that you cannot, it's a noisy outcome, and still you would like to be able to extract some information. TDA, these two steps allow, has this effect of, denoising. But here's another thing. So there's a classification. Time series of vector spaces are objects which are considerably easier than time series of simple. For example, this is because we have a classification. Any time series of vector spaces is a direct sum of bars, so-called bars. Those are the simplest time series of vector spaces, where at some point you start with one-dimensional vector space and you continue for a while, maybe infinity, but you continue for a while to be this one-dimensional and then become zero again. So what we achieve simplification. These two steps, we have a denoising effect, and we have simplification. We convert this complex world of universe of distances into much simpler object, and we also denoise things. But so for analysis, however, this is not yet enough, because what we need to transform the results. We need to find a transformation into objects on which we can do statistical analysis. If you look at the time series of vector spaces, this is very difficult to do. We don't know how to do average. If I give you, two time series of vector spaces, ask you what is the average between them, or I give you a family or an event consisting of time series of vector spaces, it will be very difficult. It is impossible to say what is the average time series. Okay, to do statistics is very, very hard with time series vector spaces, which means that we need additional transformation that would convert these time series of vector spaces into universe where I can do statistics, where I can do averages, calculate the expected values, look what is the null hypotheses, maybe calculate p-values, etc. Okay, that's absolutely essential for topological data. So how are we going to do this? How are we going to extract, statistically viable information from this time series of vector space? So we will do it through the hierarchical stabilization process. Okay, so imagine you find yourself in an unknown universe, maybe universe of biological micro world or somewhere else. So you find yourself in this universe. Okay, objects on this universe are, that's where you find yourself, and you are just alone. This is the first time you are there. So what is it that you do? The first thing you do, that you start maybe counting. You start looking at the objects. You start assign some simple counts. So let's say assume that we have some function, okay, that assigns to elements of your universe, to object that you found yourself, some numbers. Okay, so that's the first thing you do. What is the second thing you do when you find yourself in this unknown universe? The second thing you might do is to start measuring things. Okay, maybe come up with a unit and start measuring things. So what you need, start comparing things choose a distance. Okay. Now, so choosing a numerical invariant, very simple. Often this R would be very simple invariant, just some numbers, some simple numbers, simple counting numbers. And a distance, this already allows you to do statistics. Okay? And how can you do this? Here is you convert that information into a new function, a function that transforms t no longer in natural numbers, but in something in a space which is much more interesting, into a space of functions. Real to real functions. Okay, and here's the definition. Maybe it's better to look at this picture. What this definition tells you that this object, you have x, you transform it to a function, so you have to tell you what is its value. So you look at this object, you use the choice of the distance to look at the disk around x with that radius, and you minimize that function r on that disk. You minimize r over disks, and you see how this minimization changes when t changes, when you enlarge your disks. Okay? So now, so you convert this this counting invariant together with a distance into this function that map t into a much more interesting space. Okay, into much more interesting space. Now, from the point of view of optimization, this is quite this might be quite encouraging, because typically the disks are convex sets. If your counting invariant has some convexity or convexity assumptions, such minimizing over disks should be a doable problem. The reality is that this is the case if your universe has a linear structure, and that is not the case for topological data analysis. So although the minimization problem looks interesting, it is actually quite a challenge in this context. Okay, so what happens? This process of transforming a very simple counting invariant and a distance into this R hat, which I call hierarchical stabilization, has the following property. This function turns out to be Lipschitz, to be continuous with certain Lipschitz with certain coefficient, where you, with respect to the chosen distance d on t and the standard LP distance. That means that you can think about this hierarchical stabilization as modeling your universe. It's a simplification. You change this map R hat, takes an object in T and assigns a function. And suddenly you find yourself in a space of functions that have been studied for a really long time. We understand a lot of probability theory on such functions, a lot of statistics of such functions. Okay. So you should think about the choice of a counting invariant, a choice of a distance allows you to model your universe, your unknown universe, by functions. Okay, by functions. Okay? So what we are going to do, we are for our universe, we are going to take this time series of vector spaces. Okay, that's your unknown universe. Okay, so these time series of vector spaces are vector spaces where you can add vectors, you can multiply by scalars, but here you have another possibility of moving along with time. So you can use that to define a counting invariant. As for a vector space, we have a base. You could also ask, oh, now I can add, I can multiply by numbers, and I can move in time. And I would wonder, give me the minimal number of generators that using these operations, not just addition, not just taking linear combination, but also moving in time. This so the rank is the minimal number of elements that generate the entire time series using those, the standard linear combination where I can plus the moving in time. Okay? So this is the simplest thing you can say about a vector space or a time series of vector spaces. Okay, and actually, if you have if you are given a time series of vector spaces, it's actually not a difficult task to calculate. It's not computationally heavy. Okay. So I have I find myself in this universe of time series of vector spaces. Now the next element that I need is distances. Remember, I need two elements: counting invariant plus I need to choose a distance on my universe. Okay. So to choose that distance, to generate such distances, I will introduce something that I call a contour. Or other people call it a lax action of the additive monoid. That's a wrong article. Of the additive monoid of real numbers on the poset of real numbers. So what is such is a function. Okay, you act by this additive monoid on that poset. So what does this mean? It means that it preserves the order relation. If x is bigger or equal than y and t is bigger or equal than s, then acting by t on x has to be bigger or equal than acting by s on y. Okay, it preserves the order. It's an action. That means that if you act by 0, well, it's a lax action, okay? In this talk, I'm not considering actually lax, so you can assume if you act by 0 on x, you should get x. Here, I'm also allowing that you can move a little bit further away because of laxness, but you can just assume that's an equality. And the second option is that if you act by t and then act by s, there is a relation to acting by t plus s on x. If it's an honest action, it will be an equality. For lax action, it's an inequality. Okay, So here's an example. The reason I'm mentioning contour, because it turns out that there is a map. Every contour leads to a metric on a set of time series of vector spaces. Okay. Now I'm not going to explain to you how a contour, if I give you such an action, how it leads to a metric, because you see, I need that metric to define this hierarchical stabilization. I need that metric in order to minimize the rank in these neighborhoods. And I will, so instead of going through details of how to explain how a contour leads to a metric, I will give you directly a formula how to calculate this minimization, okay, in a second. So then you might say, this is like a basic elementary question. You sort of ask, do I know any action of a of a real line on a real line. So one basic action, of course, is if you act if acting by t is just adding. That's a typical action. Okay, that's a very simple action. Okay? But here's another way. Of course, you have exponential action where acting by t is you multiply by the exponent by e to the t times x. Okay? Times x. All right. But here's another way of constructing such action. If you choose a function that you call density, a function with it has to be integrable function which is positive, then you can define the action. So what is an action of t on x? You start moving until you hit a point where the area under this function is equal to t, this element you act on by. Okay. Now this turns out to be an honest action. Okay. So in other words, every positive function f leads to an action, leads to a contour, which leads to a metric. Okay. In other words, there is a space of interesting metrics on this time series of vector spaces. There's a space that includes a very rich space of functions, okay, of positive value functions. Okay? All right. So you could sort of imagine that depending on your problem, you might choose different metric. Okay? You find yourself in an unknown universe. And remember, we use this time series of vector spaces to model our experiments. We convert distances to time series of vector spaces. And imagine that the way that, let's say, industrial experiment leads to one particular time series of vector spaces, and biological experiment leads to another time series of vector spaces, and from some freaky reason, because we normalize, because we like to because we denoise, because we like to have numbers from 0 to 1, the values coming from industrial experiment and from biological experiment are very similar. And yet maybe to compare results coming from industrial experiments, you might use different metrics than to compare results coming from biological experiments, even if they sometimes might have similar values, because we use normalizations. Okay? So you should choose your metric the way you measure similarities or dissimilarities of time series of vector spaces based on your experiment. Okay, based on your experiment. Okay. So in other words, for every positive function f, we can transform time series of vector spaces by taking hierarchical stabilization of this rank, of this the simplest counting invariant related to vector spaces, like dimension or the rank. We can transform this time series of vector spaces into a space which has which we've studied, probability of this space. We have been studied for a very long time into space of, real to real functions. Okay? To real functions. Now, this modeling of time series of vector spaces is quite effective. For example, two time series of vector spaces and x and y are isomorphic if and only if for every positive function their shadows are the same. That means that if you want to distinguish two time series of vector spaces, you will actually find a function such that which leads to a metric for which these invariants, this modeling actually will distinguish between these time series of vector spaces. Okay. So if you, of course, if you have infinite time and if you have and you can use all your possible functions, you will be very effective. Whether you talk about time series of vector spaces or whether you talk about these functions, it's the same. They contain the same information. Okay? So I did not tell you how. I did not tell you how contours and these actions lead to a metric, but because I can tell you directly how you can calculate the rank of this stabilization of the rank. So for that, however, you need to decompose your time series into a barcode, and then what happens is this stabilization at time t is certain bar count. Okay, it's number of bars such that that integral is strictly bigger than t. Okay, strictly bigger than t. So you can avoid describing this metric. You might sort of can calculate this invariant directly. But of course, I could define you this invariant right away, but you would not have this story behind it. The fact that we actually try to understand this universe of time series of vector spaces by these minimizing over these growing disks and having for free, for example, stability. Okay. All right. So let me. So remember that was the TDA pipeline. We start distances. We convert them into time series of simplicial complexes because it converts noise to homotopy relation. Then I use homology because homotopy relation is converted into equalities. And now I can choose a positive function. But you see, now I have to, I'm still finding, I achieve simplification, I achieve denoising, but I do not achieve ability of doing statistics. So to do that, the next step is to choose a positive function and to model, to model these time series of vector spaces by these stabilization of the simplest invariant called the rank. Okay. And this process I call homological modeling. Okay, homological modeling. You transform distances into functions. Okay, distances into functions. Now, this process, what we achieved is we achieved simplification. We definitely end up in a world that is much more simpler than the original one, the world that we actually feel very familiar with. Okay. We achieve denoising because the first two steps already achieve this, and also we achieve ability to do statistics. Okay, ability to do statistics. Now, this ability of doing statistics allows us to have the following, to perform the following steps. For example, you might sort of try to, have your distance and try to calculate that function, okay? This stable rank for various degrees of homology. Or, because we can do statistics now, we start with a distance, and instead of doing this globally, maybe if you look at the space, let's say if you look at the space, instead of looking at the global space, maybe you look at the subsets of certain size of your space. Okay? So we might consider a bunch of subsampling of your distances, of your distance space. Instead of looking at the entire global distance space, I can look at the collection of 5-element subsets of your distance. Okay? And for each of these subsampling, I can use my homological modeling to get 3 functions. Okay, f, g, and h. Okay. Now, because I can do statistics on this, I can take averages. What I could do, I can average them. I can add them divided by 3 and form a new function. And here's another way that I also call homological modeling. Okay, you now transform this distance into a new function. by considering not the global distance, but subsampling. Now, this also has additional property of denoising. Okay, additional property of denoising, denoising property. Okay, so here's an example of this. Here's an example of this. Okay, yeah, fix a choose your figure. This is like a toy example. This is your object. This figure, and choose 1,000 points with normal error for each of this shape. Okay. Now the next thing is from these 1,000 points randomly. Okay, 100 points randomly, and once you do this, you calculate this homological modeling for H1, for H0. So that's a function, and take the quotient. Okay, so this is a new function. All right, and here the standard noise that what I'm using this additive, the function which is constant. F is the function which is constantly 1. This is this additive action. Okay. Now do this, repeat this 40 times, and then take the average. Okay, take the average. So we try to understand not how this space look like, but how the subsets of size 100 in that space look like, and what is the expected geometrical signature, this homological modeling signature for a random subset of 100 points in that space. And here is sorry. All right. And here is the way it looks on the you see changing figures, and on the right you see the signal, the modeling of whatever you see on the left. Of course, it's a simplification. You convert some complex information into something much simpler. Okay, much simpler, but maybe still informative. Okay, maybe still informative for your purposes. Okay. Now let's look at another way of using ability of doing statistics. So here is assume that here's your data. Here's your data. It's a distance on these point cloud. Okay. So you choose one point. And you might look at its neighborhood. You might look at its neighborhood with some radius. Okay. And when you look at this neighborhood, now you can use your homological modeling to assign that to that point the geometry of its neighborhood. Okay, the geometry of its neighborhood. It could be averaged, or it could be global. Okay, and we take another point and we do the same thing. We look at its neighborhood, and we assign via our homological modeling another function. Okay? In this way, we can use homological modeling to map that original data by functions. Okay, by function. Okay. Now, so what happens is that you imagine you stand in this you are in this universe of this point cloud. So you stay in your point and you see, what is the geometry of my neighborhood? Okay? And to that neighborhood you assign some function. Okay, via this homological modeling simplification. Okay, that's just a tiny bit of information that somehow describes what you see around. But maybe you might do another thing. Maybe you stay in that point and you look. You are not interested in your nearest neighbor. You are interested in the sort of annulus a little bit further away. Something that you see on the horizon. And you wonder what is the geometry of that annulus. Okay, what you see on the horizon. And again, you can either global or this average, and you just look at in code the information about that point by a function that described by this homological modeling function that describes that annulus. That's just a little speck of information describing that annulus. And you do the same with another point. You look, how does this annulus, how does this horizon looks like for this other point? And you again use homological modeling to extract some piece of information from that neighborhood. Okay. And in this case, you get another map of your data into space of functions. Now, it doesn't, we might, on the other hand, we might take a point and we might look at both of these neighborhoods. You might be interested in like what's happening in your near neighborhood and in your around neighborhood. You will model your point in your data by two functions. Okay, and you do the same with another point. In this case, you model your data by pairs of functions. The space of functions square. And you can explore this way, you explore geometry of how points are embedded in your space. Okay? So you can so in other words, so you get these functions, okay, but you can use it further, this exploration you can use further for example, for dimensionality reduction. So let's assume that we modeled this in the way I just described. We modeled this by three functions. I look at three different neighborhoods, and I model this by three functions. Okay, how the points look like, in the nearest neighborhood, a little bit further away, and really far away. Okay? Now, so to each point you assign three functions, and then you might map these three functions to, for example, take the first function, take a sort of affine plane. Okay, you look at these space, and you look at the distance from the first coordinate to the second. Let's say L2 distance, and the L2 distance from the first to the third. Now you get two numbers. Okay, L2 distance is integral of it's an integral L2 distance between first function and second, first and the third. Okay, and you get two numbers, so map into R2. Okay, so let's try to do that. Let's try to explore the geometry of high C contact map. Here's this contact map of this human neuron that we got from our collaborators and SciLife Labs. And remember, I converted that information into this similarity. I need a distance for this process. So here's the recollection of the distance. I'm doing this strand of DNA, and I'm counting from that loci what's the difference between the connections to itself and to the previous loci. Okay, so this distance is of that size, 3,274 times 3,274 loci segments. Okay, so we do homological modeling. Actually, in this case, I will choose 22 different regions. This particular case, I chose 22 different regions for each of the points, and I use first 22 is using H0 homology, zeroth homology, and the second 22 is using H1 homology. Okay, H1 homology. So here are examples of how these functions look like. This is the third. That's the third coordinate. Those are the functions. There are 3,274 functions. Okay, that's how that space via that modeling, when I project on the third coordinate, that's how this distance is mapped to these functions. That's the fifth coordinate. That's 13th coordinate. Okay, that's 13th coordinate. Okay. Now, what we could do, you can start doing conclusions. These functions describe somehow the geometry of embedding of each loci into this whole space given by this similarity D. Okay, but let's look this dimensionality reduction. Let's look at the distance of this third one to the fifth and the third one to the 13th. Okay, and here is the outcome of that dimensionality reduction. Okay, you can see that somehow the space, you might sort of have a feeling that this space of this dissimilarity, this space of these segments in DNA has several, at least, 3 different interesting components. Okay, or 4, even 1, 2, 3, 4. You can sort of think about, okay, these loci somehow are closer related than these loci, and then these loci versus, these loci. Okay? There's some geometry that you suddenly discover, you feel more familiar, and you might wonder, like, what is so special about these loci? If I take a high C contact map of other tissue, will this be similar or not? Okay. All right. So let's look at the other coordinates. Those are, remember, from first 22 coordinates. Those are H0 stable ranks, H0 homological modeling for various regions, and for the same, from 22 and above, so 23 and up to 24, those are H1 for the same regions. Okay, so I take the same. Those are the same regions. Those are the same regions that I've used before, except those are the signatures. Those are the homological modeling of in degree 1 for H1. Okay, that's how these functions look like. And then you might sort of see, okay, let's find dimensionality reduction. Okay, exactly the same thing. Take the distance of the first of the 25th coordinate to 27th coordinate, and from the 25th coordinate to 46th coordinate. And here's the picture. And again, based on H1, on the way on this H1 information, we again see that there is some interesting clustering happening. That certain loci in this DNA strand, they group together because they have a similar contact information. Okay, similar contact information. All right. Let me present another example of how one can use these homological modeling. Let's consider Wisconsin breast cancer data. That's a very old, very classical data. It's 699 breast cancer patients described by 9 real valued characteristics of cell nuclei. So what happens is that there's a very fine needle. They would take a biopsy and they would photograph that, and there would be actually a person looking at this. That's how this data was formed. A person looking at this picture and values. There was some. How well defined are the borders, density, 9 values. Okay, and based on this. The idea was, can we, based on this picture, can we decide whether the tumor was benign or malignant? Okay, so standard methods, you can use machine learning, you can use k-nearest neighbors, other methods. You get around 86% accuracy, which is slightly above what these practitioners at that time were good at. Okay, around 86% accuracy. But what does this geometry exploration can give you? Okay, so it turns out that so I'm not describing which regions I'm taking, but if you look at H0, it turns out that this space. So for you look at this space of these 9 measurements, and you look how these space measurement is embedded into this space. And by exploring that space of these breast cancer characteristics, it turns out that the points in this landscape, the points split into 3 groups. There are 3 groups. This is this group, this is this group, and there is this 0 group. It's not well written. There's around roughly 1/3 of them. Some of them are a little bit larger, but there's also a substantial group that it's just 0. It's not visible. And then you color it, you color red to be malignant and blue to be benign, and you discover that this separation is perfect. That group, there's one red if you see well. This group almost entirely consists of benign, and this group entirely consists of malignant. Okay? So now what's left is this group that 80 forgets. 80 forgets. Let's just look at H1 modeling of just that those patients that H0 forgets. And you draw, and you'll sort of see that there are also, three groups actually. There's this group, there's that group, and there's something that you cannot decide because there are 0. H1 also doesn't distinguish. And then it turns out is that color, and then you color, and blue is benign, red is malignant, and again you discover that particular group here is almost entirely benign, and that particular group is almost entirely malignant, and the rest of it turns out to be around 13%. So you get roughly similar accuracy, the geometry, but at the same time you discover that these 9 value characteristics, these characteristics of these breast cancer patients, naturally splits into 2 groups. There are benign and malignant split naturally into groups, and it would be interesting. We didn't get information about this. It would be interesting to see some clinical information about these patients. Why do they split in so? So you don't get better accuracy, but what you get, you can explore the geometry, and this geometry can be quite informative about your data. And I think this is it. Thank you for your attention.
Oh, let me clap for everybody. Really, thank you for this very passionate lecture. I want to know more. So do we have any questions for Wojciech? Just speak up.
I have a fair standard question, if I may.
Yes, please.
So, Wojciech, what you just told us, how could you generalize it for multi-persistent TDA, like say two-dimensional TDA? Because you base the first exposition on the barcode decomposition.
Right. So far, I mean, remember, I've been very careful. I only it was at only one point that I mentioned this bar decomposition. You see, sorry, let me just
on
go
the stable
here.
rank
Okay.
invariant.
Exactly. On the question is how do I calculate this stabilization? That's the key thing. How do I calculate this stabilization? And of course, like I was very, very careful not to use bar decomposition as little as possible. Okay, and it turns out that so in the case of one persistence, destabilization, destabilization can be written in the terms of bar decomposition. Okay? Now, for two persistence, I mean, everything what I told you, it works well, except that I do not know how to calculate these functions. Now, to calculate them exactly, it is an NP-hard problem. But you see, I define this stabilization. You see, another thing, I define this stabilization as it was defined, this stabilization, as certain, minimizing problem. So how would you minimize this? how would you minimize? Sorry, I should have. How would you minimize this? One aspect could be the following: if you are able to randomly choose a point from that neighborhood, you can do. Let me take a random point, calculate its rank, which is a fast calculation. Take another point, calculate the rank. Take another point, calculate the rank. Make it, do it for a long time, and then after a while, say, "Oh, I'm satisfied with the minimum I found." Okay? For several purposes, that would be good enough. The thing is that I do not know how to randomly sample, how to randomly sample the time series of vectors or 2-parameter time series of vector space. But what we've done experiment with, you see, remember that this whole procedure is you see. I want to calculate this stable rank, but I could try to stabilize. I could try to stabilize, the rank of that whole composition. And these experiments we can do. Because here I can choose in and I look. Let me choose a random distance by adding some noise that I'm sort of might expect what this might be, and then find the smallest rank of these calculations. That I can do, and it definitely shows that by choosing, after a while, it's for various purposes, for various experiments that we've done, this is enough. Okay? I do not know how to choose from a random neighborhood a time series of vector space. If you give me a time series of vector space, I would like to say, construct a random time series of vector space that is at the distance at most t. That I do not know how to do. But we might have some tools to do this in the future.
Okay, just you don't know how to take it randomly, both in the 1D and in the.
No, in 1D I know. In 1D, I know,
yeah.
because I look at the bars.
Okay. So for a two time series,
in 1D, I even have a precise statement, precise value of the stabilization of the rank in terms of bar decomposition. I even have a precise thing. But because I have a barcodes, because this is a space of this is barcodes. This is a subspace of multisets, okay, in the part of the plane, and that choosing randomly there, I actually know how to do. Okay,
it's clear. Thanks.
I have a stupid question. Why the size of the matrices is 3274? 3000?
That was I don't know. That's the data we were given. Okay, so. This high C that we get, this high C was of that size. So each of them was around, as I say, 1 mega bases. Okay, 1 mega bases. You look at this trend. So those are not genes, right? Genes can be short or long. This is, you just look at these segments of the same size. Okay, size around 1 mega base. Okay.
You didn't make a choice. This was given to you.
Yes, no. I gave you a Wikipedia thing about high C contact map. I'm a mathematician. The thing that I was given, I'm giving this matrix, a contact C map, and they say and they of course they explain to me, tell me what it means geometrically, etc. And so there was a natural question to try to explore the geometry.
I see. Thank you. Okay, do we have any other question?
Hi, Wojciech. Hi, everyone. Very nice talk, Wojciech and Claudia. I have a question. It looks like in the breast cancer data set, you refine the analysis or the discrimination, the classification, varying the degree of the homology. It's like in the Fourier analysis, you are looking for something more refined. Do you think that going on beyond degree 1 would help refining the analysis? And the second question is it why not changing maybe the function for the rank, stable rank?
Yes, for stabilization. Yeah. So right. So yeah. So I mean, I agree. I mean, like looking at the zero homology and the first homology and the second homology, this might give you more information. Okay. Look, this was. I mean, I give you like we. Okay, I and people at my group and collaborators went through like literally hundreds of examples, and it's not that every example looks like so pronounced. Okay, I gave you successes. Okay, successes which is majority of them are very very few. Okay, but sometimes you get this very pronounced. I think that sometimes H0 gives you something, and then H1 can refine that thing. Okay, but I don't have mathematical explanation for this. Okay, this is just sort of I have several examples that when this happens, we are us, right? We've been like, oh wow, it's sort of I wouldn't say astonishing, but it's very surprising. Okay. Particularly since, for example, with Wisconsin breast cancer, I don't think people were aware that there was like a natural split. I mean, it could be that one of them were, old people, one of them were young. I mean, it could be old data set. It's a very like old, maybe 10 years or 13 years old Kaggle data set, and this is a typically thing that an example that I go in my course on TDA at KTH. This Wisconsin breast cancer, but again, I don't have a good explanation. When I get the data, like if you look at this high C, for example, there was no way that I could predict from the beginning that homological modeling will be in any way informative. I know that there is a large component of noise, so that's already quite encouraging, because you see, if there's a component of noise, like a standard statistical methods are very hard to extract something, because you repeat that experiment. So there's a high component of noise. So that means that that suggests to me that this method might be a little bit more informative than other methods. Okay, but it's still and it might give it might be informative or not. But of course we try. We have to choose F. Plus we choose, remember, we geometrically explore. We look at the embedding of a point in your data, and we look how it looks around, how it looks a little bit further. You can have different neighborhoods, okay? And that's you try different contours. How do you say? We don't have automatic choices with contours. The trouble with contours is that we don't have automatic choice. Machine. What we write right now, what we do, I will sort of run 1,000 different functions and choose the one that gives you some more interesting results. Okay, that's the current way we do this thing. Okay. But it's actually interesting. This thing is really cool to do it also, for example, on NIST data. You see, when you look at the NIST data, it is not about, you see, when someone, so this is a typical student's approach, right? I give my students, you might sort of look at the NIST data, and they would take a number 6 or number 8, and they say, I will look at the geometry of this number 8. It has 2 holes. But that's not the way we understand that thing, right? It's about the space of all the numbers. I write 8 in different way than someone else, and still I know that there are certain limits. How badly I can write my 8 and still be, informative that 8 is 8 actually. Okay, so this is the relation. This is the space of these numbers. And one can then explore, one can take a number and explore that space, how it looks, right? And it's actually very interesting. And you can sort of get get another view of it's not the individual, it's about this relationship. When the 8 becomes 6, When is it? When is the border that, you know, what is the neighborhood of 6 and what is the neighborhood of 8? Exploring spaces, and I believe, you know, these TDA invariants actually can be quite informative for that purpose. It's a long answer. Sorry.
Okay.
Thank you. Thank you.
Okay, we thank you very, very much for this very nice talk.
It was a pleasure. Thank you.
Oh, sorry.